move on to discuss the geometry of linear regression, or OLS, and a particular issue that occurs, a certain type of instability that occurs in OLS or linear regression, the OLS or linear regression solution. They're both the same, the Moore-Penrose pseudo-inverse. And how the ridge and lasso variants of OLS or linear regression interact with this instability. Do they promote it? Do they ameliorate it? Let's see. And that will lead us in the end to some other whole spectrum of different methods. So in order to fully understand, right, we're going to need to do a couple of things, at least a couple of things. The first one is we need to understand collinearity and why that leads to instability. But before we can understand that, we need to understand something of the geometry of linear regression. Right, so now we're going to start making things more precise, not this touchy-feely, hand-wavy stuff. And then we will see how ridge and lasso, we also need to see how they affect the geometry of ordinary least squares or linear regression, if they affect it at all, in actual fact. One of them does, the other one doesn't. I won't tell you which for now. Okay, at that point, we can start to look at some extensions, improvements to potentially improvements to ridge and lasso, namely elastic net and a few others like group lasso, sparse group lasso. Okay, so let's start with looking at the empirical risk, rewriting it. I want to rewrite it as follows. So n times the empirical risk is this quantity here. Now, what is this quantity? Well, let's see what this quantity, let me write it up here. So this is phi theta minus y, dot product of that with itself, phi theta minus y. And what's this going to give us? Well, it's going to give us phi theta transpose phi theta, right? And then we're going to get minus, I did this earlier on, so I'm going to skip one step here, minus twice, we're going to get, now what's the best way to write this? We can write this as phi theta transpose y, right? Plus y transpose y. Now the key thing is here, these are the only terms that depend on theta. So we can call this just plus constant, right? Meaning doesn't depend on theta, no dependence, right, on theta. Why do we care about that? Because this is what we're minimizing as a function of theta. So if we have something that doesn't depend on theta, well, we just get rid of it anyway, because if we differentiate it or take its gradient, it's going to be zero anyway. So we can discard it. Now, this, we can also write this, which is this squared norm here, the 2 norm, this is the standard norm, like this. Right? So I'm doing a little trick here, performing a little trick. So theta hat here is our OLS solution, which is phi transpose phi inverse phi transpose y. Now, so why can we write it like this? Well, let's look at the terms only that depend on theta. So this constant here means, same as here, doesn't depend on theta. Well, let's multiply this out, all the terms that depend on theta only. So we're going to get this transpose this times this. So we're going to get theta transpose phi times theta, right? So that's this times this times this, and we're going to get minus this times theta, because that depends on theta. So we get minus theta at transpose, which is our OLS solution, phi transpose phi times theta. And then we're going to get minus plus this times plus theta transpose this times theta hat. So that will also result in a minus. There's a minus there and there's a plus there. So minus theta transpose phi transpose phi theta hat, right? Now, these two are going to turn out to be the same, right? That's easy to see actually, because we can write this one here as phi theta hat all transpose. So that's this one and this one. What I've done is that's phi transpose phi, yeah, times this phi theta. So we got this vector dot this vector. It's the matrix times vector, vector, which is the same as this because this is phi theta all transpose times phi theta hat. So it's this dot this, which is exactly this dot this, which is what we have here. So they're the same. So we can write this as minus 2 times this. Now what's this? So remember the rest of the term, the other term here, this times this times this, is not going to depend on theta. So that's in this constant. We can put it in this constant, meaning no dependence on theta. So what's this? Well, this term here, here is phi theta transpose times phi theta, right? Which is exactly this term here. So these two match. What about this term here? We're going to have minus 2 theta transpose phi transpose phi times theta hat. But theta hat is our OLS solution, which is phi transpose phi inverse phi transpose y. Well, that cancels with that. That's the inverse of that. So we're left with minus 2 theta transpose phi transpose y, which we can also write as minus twice phi theta all transpose y, which is exactly what we have here. So those two can match as well. So we can rewrite n times the empirical risk, which is this, like this, where this is our OLS solution. And this constant means terms that do not depend on theta. So they're not necessarily constants as such. We're saying as a function of, this is a function of theta. This has no dependence on theta. So when we minimize this, when we differentiate it or take its gradient, is going to go to 0 anyway, so we can ignore it. The only part that matters is this, excluding this times this times this, which also doesn't depend on theta. But there's a reason why we're using this little trick here. This is a common trick, actually. We'll see this again in Bayesian linear regression. Now, the level sets of the empirical risk, I defined these before, are these sets. Theta such that the empirical risk is some constant, right? So we can write this as, because Rn, we've just seen, can be written like this, or n times Rn. Or so we can write Rn is this divided by n, right? Plus a constant divided by n, doesn't really matter, right? So Rn equals a constant is the same as this equals some constant. So the level sets of the empirical risk are sets that look like this. And these are ellipsoids centered at theta hat. Now you can understand why I was showing you that picture earlier, right? Now, the axes of these ellipsoids are aligned with the eigenvectors of this matrix. Right? So this is all explained in the linear algebra videos. I'm not going to re-derive everything here, but I will explain step by step, and then you can go and check out the linear algebra videos to see proofs of all of these. So the ellipsoid axes, right? So when we saw in the 2D case, we saw an ellipsoid like this. The axes are this axis and this perpendicular axis here, this is perpendicular, this is aligned with one eigenvector, let's call it V1, and this is aligned with the other eigenvector V2 of this matrix. In 2D, we're looking at the 2D case, phi transpose phi. So here, this we're looking at theta is in R2. Right? So this is what I mean by axes are aligned with the eigenvectors of this matrix. So these are the eigenvectors. We're going to see this anyway. We're going to discuss it in more detail. So let's have a look at an example. It's the best way to see it. All right. We're going to consider a 2D case. Let's stick to 2D. Let's say that our matrix phi transpose phi. Now remember, this is a symmetric positive definite matrix. Right? So it will have a form like this. This is symmetric. Right? If we transpose this, we get back to the original matrix. You can see that. Why is that? It's obvious, right? What's the transpose of phi transpose phi? Right? It's going to be this one transpose and then this times this transpose. Phi transpose transposed again, which is just going to give us phi. So we get the transpose of this matrix is itself. It's symmetric. Right? And it's positive definite, which is something that I think I showed earlier on, but at some point we will show it anyway. So what will these look like in that case? Well, I'm not going to write it all out, but they will look like this. Right? They will take this form. So this equals a constant where we're going to, for this, we're going to use this 2 by 2 matrix. We're considering theta equals theta 1, theta 2. Right? It's this vector. Has two components. So if we were to do this, so the transpose of that is this row vector theta 1, theta 2, to multiply that by A, B, B, D, and then multiply that by theta 1, theta 2, and you'll get, and that's equal to some C, we'll get this equation here. Right? I'll let you do that for yourselves. It's just algebra. So what is this an equation for? This is equation for an ellipse. This is an equation for an ellipse. And unless these two are both 0, this ellipse is not going to be aligned with the axes. It's not going to look like this. It's not going to look like this or like this, right? It's going to be tilted, right? It's going to be tilted at some angle. Okay. Now, we have a symmetric and positive definite matrix, which means, again, this is all in the linear algebra videos. Look at the sections on eigenspectra and diagonalization. It's explained in there why we use this name as well in great detail. So we can diagonalize it because it's symmetric, positive, definite. What does that mean? That means we can decompose it. Well, there are equivalent forms, but this is the most common form. We can decompose this matrix. Let's just call it A. We can write it as, so A is this, some matrix Q times some matrix lambda times the same matrix Q transposed. And this matrix lambda is a diagonal matrix. Looks like this. So this is the matrix lambda 1, lambda 2, because we took a 2D case, and everything else is 0. A diagonal matrix is a matrix where only the diagonal terms are non-zero. And we often write, rather than writing this out, we can write it more compactly like this. Diag, the first term in the diagonal is lambda 1, lambda 2. And we might write things like this as diag lambda 1 to lambda n, right? In that case, there'd be an n by n matrix. That would be lambda 1, lambda 2 down to lambda n. And everything else is 0. This notation here is common for that. So, so we have this special form. This is called an eigen decomposition of this matrix. So these lambdas are the eigenvalues in this eigen decomposition, eigenvalues of our matrix phi transpose phi, our symmetric positive definite matrix. Right? The columns of Q are the eigenvectors. This one corresponds to lambda 1, and this one, the eigenvector, corresponds to lambda 2. And these will be in R2. So the VI are in R2. They have two components. Right. So this matrix has orthonormal eigenvectors. That means V1, we're using the standard in the product here, transpose V2 is 0, and V1 transpose itself, or dot product with itself, is 1, and the same with V2 with itself is 1. But V1.V2 or V2.V1 is 0. Right? So these are orthonormal, these eigenvectors, and they correspond to these eigenvalues. So this matrix is what we call a unitary matrix. Again, watch the linear algebra. This is explained in massive detail, meaning that Q transpose is going to be equal to the inverse of Q, and this is something we'll use later on. So in this case, for a unitary matrix, its transpose is actually its inverse. Right? Nice little matrices, these unitary matrices. Right? So we've got this diagonal, we call this a diagonalization of a symmetric positive definite matrix, meaning we decompose it like this. A matrix consisting of its eigenvectors as columns times a diagonal matrix of its eigenvectors times the transpose of that first matrix, which is unitary. Now we can define new coordinates. Right? We're going to change the coordinates for theta, right? Our vector theta. Rather than this vector, we're going to instead use this vector u equals u1, u2. Right? And how do we get from theta to u? We use this rotation. It's a transformation. It's the matrix Q transpose times theta minus theta hat, our OLS solution. So if we have a theta, we can get the corresponding vector u by doing this. So whatever theta, let's say theta star, we get the corresponding u star by this transformation, which is actually a rotation. It's a rotation of theta star. It's rotated somewhere. So, okay, where is this taking us? So in these new coordinates, what does this look like? Well, our equation for an ellipse, what does it look like? The contours of constant empirical risk. Well, let's think, right? So we've got, well, what do we have here? We have theta minus theta hat times this. Well, what's theta minus theta hat? Well, theta minus theta hat, according to this, is equal to u, right? It's u times, now, q transpose, let's multiply both sides by q transpose to the minus 1. Q transpose. So we're multiplying this side by this, which is going to cancel that. So we're going to end up with theta minus theta hat. And then we have to multiply this side, u, by also q transpose to the minus 1. Now, q is unitary. And so we get q transpose is q minus 1. And we're taking the inverse of the inverse, which is going to be q. So this ends up being q times u. Right? Okay. Actually, thinking about it, we could go a different way around. Or could we? Actually, yeah, maybe we should simplify this. Or should we carry on with that? No, let's try to simplify this, because we've got this decomposition. Maybe that's what I'm missing here. Even I've forgotten how this happens now. So this is Q lambda Q transpose, that's this, and that's multiplied by theta minus theta hat transpose, or perhaps we use them both together, theta minus theta hat, right? So what have we got here? Well, we've got theta minus theta hat transpose times Q. Well, that's theta minus theta hat transpose times Q. That's this with this, and then we've got lambda. So let me separate this. Well, what's this? That is the transpose. This is the transpose of Q times theta minus theta hat, right? Transpose. It's that transpose, because we would get that transpose, which is that, times Q transpose, which is Q, right? But what's this? Inside here is U. So this is U transpose. So we've got this is U transpose. Now we've got lambda here. Now we've got Q transpose times this. Oh, that's just U. So this is just U, right? So what was I doing here? Something silly. Okay, so actually we didn't need to do any of this nonsense. It was just simply came out of here. So what we've ended up with is U transpose lambda U, which is exactly what we have here. Okay, let me hide all of this nonsense. So now we see, let me just go through it again, since I wasted so much time. This is just Q lambda Q transpose. This is multiplied by, so this is this from this eigen decomposition, theta minus theta hat times this, and that's transposed, times theta minus theta hat. Right? Now this thing here is U. That's U. So we've got lambda times U. Now this thing here, what's this? We can write this as Q transpose theta minus theta hat. Transpose, sorry, all transposed, which is U transposed, right? Because what's inside here is exactly U. So what we end up with is U transpose lambda U, which is what we wanted. Which is what? Well, it's going to be lambda 1. So let's write this out for the sake of completion. So we've got lambda is lambda 1, lambda 2, 0 and 0. U transpose is U1, U2, right? And U is U1, U2. And if we multiply all of this out, we'll get this, because these off-diagonal terms are 0. This is looking nicer, right? It's looking like a standard ellipse aligned with the axes. So the ellipse equation is what now? It's this equation, right? Because we want this equals a constant. Well, we've rewritten everything by doing this, performing this transformation. We're using new coordinates. We're switching from theta to U. So in these new coordinates, our ellipse now looks like this. Our contours of constant empirical risk, they look like this. Now, these can be written in a standard form, right? The standard form for an ellipse is like this. This is the standard form for an ellipse, right? Where these A and, I call them A1 and A2 here, A and B, are the semi-axis lengths, the semi-minor and the semi-major axis lengths. We'll see a diagram on the next page. And they're given by, so according to this, if we divide through by C, divide this by C, divide this by C, this becomes 1. Then we get this divided by C over lambda 1, and this divided by C over lambda 2. And so A is the square root of C over lambda 1, and B, whichever one it is, the semi-axis, the other semi-axis is of length c over lambda 2. So let's have a look at what these mean. This is what they mean. So the semi-axis lengths are these lengths here. So they're half this length here, the shortest direction. So this we would call the semi-minor axis, and this we would call the semi-major axis. And this length here is what appears here, and this length here is what appears here, the square of this length here. And this is the standard form for an ellipse. And so in these new coordinates, the level sets, these contours of a quadratic loss, look like this, where a and b depend on which value of the quadratic loss we have chosen, the c, the little c. And here they're aligned with the axis, and they're centered at 0. This is standard form, we're centered at 0. So what have we done? Basically, we've performed a transformation in which we've shifted all the level sets to 0, to be centered at 0, and they are aligned along the axes. So this will come in handy later on. But for now, what we're going to do is move on to study collinearity